Great. Today is Thursday, April 18th. This is class 5, fifth week, and this is Thursday, the class where I tend to get it right. The Tuesday class is kind of a little more fun, but I get a lot more wrong. And by Thursday, I kind of have it worked out. And so here we will see a better presentation than the previous ones, just because I'm less wrong. So we'll start here. I'm going to start with coral reefs. Charles is here. Okay. All right, here we are. We're going to start with a short understanding of coral reefs. Contrary to what you may have heard, corals are doing really well around the world. Corals have a symbiotic relationship with a specific algae, and the algae does photosynthesis, so it provides power to the coral. And the algae gives them their color. They're called zooxanthellae. And when the conditions in the water change, if it gets too cold, a little colder, a little saltier, a little warmer, less salty, corals drop their algae friends and they wait until a new one comes along, and then they colonize that and reproduce it within their shell, condominium structure that they built. And so during that time when they're waiting for a better partner, they bleach. And coral bleaching is not death. Coral bleaching is a natural adaptation of the coral polyp changing its symbiotic algae. You can come back a month later and the coral will be back in business, possibly even wearing new colors, because the algae is what gives it the color. So bleaching is a transitional phase, not death. And they do it many, many times. They can do it several times a year. They can do it every couple of years. It's just an adaptation. So the Great Barrier Reef is, in fact, at an all-time measured high. They started measuring Great Barrier Reef cover index back in the 80s. And of course, the news is full that the reef is dying from humans causing climate change, because some reporter or some group will put out a report saying they're bleaching, blah, blah. And there's a lot of government money to protect that terrible thing, bad thing from happening. So they try to get their hands on the money to fix the problem that doesn't exist. But the reality is the corals are higher right now than we've ever measured them. That doesn't mean much. Corals have been around for 250 million years. But I want you to see that there's a problem here. I want everybody to understand that this is a problem. I think somebody's in the waiting room that I can't see. No. Okay, sorry. All right. All right, sorry, here we go. So everybody can see this. There's a problem right here. And the problem is that as soon as you start to measure something and create an index for it, and it has nothing to do with anything humans are doing, when it's high, they'll go away and they'll go after something else generally, or they'll look for whatever signs they can to pick on, like bleaching. But then at some point later, because this is more or less a random walk, it's an independent variable, it'll go down. And the minute it goes down, and here's a good example, it goes down for 1 year. If it goes down for 2 years in a row, something we have no control over, they'll just predict the end of days. They'll use that to extrapolate forever and say that the coral reef is over, it's dying, it's finished. And it's because they're looking for any trend that they can get their hands on to make these, apocalyptic predictions. And so just the fact that you're measuring something is just a setup for people who have their own purposes to use this data to do what they want with it. And any small random change, they'll grab hold of. So you just wait, you'll see. It is not over at the coral reef. They'll just grab this anytime they can, anytime they've got anything to hold on to and show the world how disastrous it is, they will use that. And data is part of one of the things they really like. So as soon as they get a little data, they're going to use it. All right. So the Earth's climate system is a complex, ever adapting machine. And the key to understanding it is heat transport. But to understand heat transport, we have to put these basics in place. And this is the carbon cycle. And this is going to be pretty simple. This is not too technical. This is the famous CO2 Keeling curve, named after Charles Keeling, who started measuring CO2 at the Mauna Loa Observatory in Hawaii in the 1950s. Now, I like to show this curve with 0 parts per million at the bottom because that gives the proper reference, and it's not a very steep curve. Now, who knows what this curve represents? Can anybody explain this curve? Anybody got this? Just turn on your mic because I can't see everybody.
I've had someone try to tell me it's CO2 going up and then making the heat temperatures go up.
Oh my God.
That's what I don't know if that's true. I suspect it's not true, but it
No.
was someone who was trying to argue with.
Right. So that person knows nothing. So
Yeah.
right. What's happening is probably there are different views on this. Javier is pretty convinced that the entire rise for the last 100 years is from humans. There are also reasons to think that there's a natural background rate of rise before that, since coming out of the Little Ice Age. It hasn't really been shown. It's still an open question. But let's say between 100% and 50% and 100% of this is from humans. But no matter what, CO2 is rising. And it's rising because of the natural cycle of CO2. So this has to do with forests breathing. When this is the bottoms are summers when plants are sucking in CO2 and they use CO2 to make glucose, which is a way to store energy. So that's how they turn sunlight into stored energy, into fuel. And that glucose then turns into plant material and leaves and wood and everything else that can burn because it's stored energy. And then in the winter, so they're sucking CO2 out of the air in the summer. And then in winter, they're exhaling, they're letting it out. And they're actually breathing in oxygen at that time. It's kind of a little bit of a burning operation within the plants. And so they're letting it out, and they're letting out and this is the natural rate, but on top of that. So think of it sort of somewhere underneath that, humans are adding some CO2. So this is not a human caused zigzag. It's might be a human caused rise. So you're seeing the summers at the bottom and the winters at the top. And this, obviously, if you think about it, is in the northern hemisphere where Hawaii is, because in the southern hemisphere, in the southern hemisphere, it's the opposite. So if you were to measure this in Australia, you'd see it offset by 6 months. Okay, these are sort of opposing stair steps because summer and winter go back and forth. And so, but overall, underneath it, CO2 is rising for whatever reason. So you more or less want to think of it as a smooth line, because the jags don't matter. The jags have been there forever. There's been seasons forever. Doesn't really matter. What matters is that it's going up, and it's gone up from about 220 parts per million 100 years ago, maybe, to about 420 today. So people say that forests are the lungs of the earth and they store carbon, but and Bill Gates says this, and it's absolute nonsense because forests don't store carbon. Forests breathe in carbon and put it into plant material during the summer, and then they release carbon in the winter. If they stored carbon, then forests would be standing on kilometers thick of built up carbon. But in fact, most tropical forests are very rocky with just a thin layer of soil on top. Forests breathe out as much carbon as they take in. They don't need animals to provide oxygen. That's a myth. They exist. The planet would be covered with living, healthy forests without any mammals. they provide, they take in sunlight and they manage the carbon cycle yearly. And then as they decompose and they rot, or when they burn, they release the energy and the carbon back into the atmosphere. So it's a full cycle, right? And so this is carbon storage. Mountains, seabeds, coral reefs, limestone and chalk. This is where the carbon is. Limestone and chalk are basically the same thing. It's calcium carbonate. It's zillions of tiny sea creatures taking CO2 out of the air. And these are called zooplankton at the surface of the ocean, taking CO2 out of the air, combining it with calcium ions that are in the water already. And they can't do it without the CO2, and they combine them to make shells. And so when we see, and we're going to see in a minute, we're going to see CO2 going down, that's shell making. Then after those things get eaten, or they just, they turn into whatever, all that calcium carbonate falls to the bottom of the ocean and creates sedimentary layers that get stacked up over millions of years to make limestone and chalk. So oceans really absorb most of the carbon, and they store it in rock, and then it comes up again and forms continents like Europe and the Middle East. Most of you right now, if you go 200 feet down below you, you're sitting on top of seashells and bones of sea life from hundreds of millions of years ago. Okay, that's where the carbon is. CO2 comes out of the earth in volcanic eruptions. So when there's plate tectonic movement, when there's a lot of plate tectonics and a lot of volcanic action, then you get more CO2 coming out from the crust, melted down into rock, and then getting released as CO2 gas from volcanoes. Volcanoes don't have much of an impact on our climate because they're pretty much always going at the same rate year round, for hundreds of thousands of years. Question? All right, so only maybe if there's like an eon of very active volcanoes for a million years, that could put more CO2 into the atmosphere. But volcanoes and sea vents put a pretty constant amount of CO2 into the air every year, year after year. Now, the main reason that CO2 is not the driver of temperature is that it never has been. And that's what we're going to look at next. I want someone who will read something. Can someone volunteer to read this, please? Just turn on your mic and read. Someone, a good reader. Joe, read.
Sure, go on. Reports from fishermen, seal hunters, and explorers all point to a radical change in climate conditions and hitherto unheard of temperatures in the Arctic zone. Exploration expeditions report that scarcely any ice has been met as far north as 81 degrees, 29 minutes. Soundings to a depth of 3,100 meters showed the Gulf Stream still very warm. Great masses of ice have been replaced by moraines of earth and stones, the report continued, while at many points well-known glaciers have entirely disappeared.
Yeah, when was that written?
You tell me.
1922.
Okay.
Yeah, this is a big weather report from 1922. It was picked up by many newspapers. It was picked up by the Washington Post. And you can find copies of this all over the place. It's called The Changing Arctic. And the alarmists say, yeah, but that was at the time, and that was very small potatoes. And now we've got so much more data. So now we have data? Great. Let's look at some data. This is a bunch of graphs that are very commonly used by us skeptics to show that there's no correlation between CO2 and temperature. And then they, we say, okay, look, see, it's anti-correlated a lot of the time. But these are not very good proxies. And so I want to show you a better way to look at this data, because this, the older it gets, the more uncertainty there is. And you can kind of combine and use these graphs to suit whatever purpose you like. So let's look at a better set of data. Now, this data comes from proxies. Who can tell us what is a proxy? Anybody? What's a proxy? One person knows what a proxy is? Proxy study? Okay, that's fine. A proxy is where you drill a hole in, could be a glacier, it could be sediments, it could be peat, because peat bogs carry a lot of information. You drill a hole, you take the hole out, the cores, and you lay it out, and you look at each layer, and you try to figure out what signals you can find in that old rock. How old is it, and what's going on? And a good example of proxy is stomata. Who knows what stomata are? Anybody? Stomata?
And ginkgo leaves.
All leaves, every leaf has stomata. A leaf has a sunny side that absorbs sunlight, and on the bottom absorbs CO2. And they do that through little tiny holes for breathing in CO2. All leaves have these. And when there are times when there's much CO2, they don't need very many holes. So you can go through the fossilized leaf skeletons and count the stomata and see that the older they get, or when there's a lot of CO2 in the air, there are few stomata. And then when there's not much CO2 in the air, then they need more stomata, like they have today. Today, leaves need a lot of stomata because we're in a CO2 famine right now. And you can go down through the millions of years counting this and try to put together a picture of CO2. Temperature is often done by the isotope of oxygen here, which is sensitive to the state of water. So you can tell when it's frozen, you can tell when it's in ice, and you can tell when it's in vapor or liquid. So this oxygen isotope is something you can also look at down through millions of years and try to tease out, when it's increasing, that means temperature is increasing and so forth. It's a pretty sophisticated science, and it works about as well as it can right now. I'm sure in 20 years we'll know even more. So now look at proxies for temperature. It's the only way we're going to figure out temperature is just to drill holes and look at the rock down there. And want to look at this one here by Royer. This is a pretty smart proxy from, I think, 2012 or something. And it's I want you to see something here. We're going back in time to 550 million years. This is the Phanerozoic. The Phanerozoic is basically life as we know it. Okay, we have the beginning of flowering plants somewhere in here. We have the Cambrian explosion, which happened in the seas, and tons of life emerged here. And if we look backwards, we see some peaks. 1, 2, 3, 4. We see temperature peaks. So we're in a temperature valley right now. We're in an ice age. And we see we're in a very hot time, temperature down, very hot, temperature very cold, very hot. And what's the spacing here? As you notice that it's pretty regular. See that? So we got 4 peaks and 4 valleys over 550 million years. And that's a spacing of about 150 million years. Anybody ring a bell? 150 million years from our previous classes? What is it that's a 150 million year cycle? Come on, somebody knows.
So that thing you had about the solar system moving through the space.
Spiral arms of the galaxy. That's the 150 million. It's 230 million years around. Sorry. Yeah, I think it's 230 million years around. It's 150 million years through the spiral arms. And that's the theory. But you have to admit that if you saw this, something is causing it. It can't be CO2 that's this regular, right? It's got to be something orbital or galactic. And at this scale of 150 million years, it's probably galactic. I mean, you can't say that it's this movement of the continents is this regular. It isn't. So something galactic is probably happening unless we come up with a better solution, a better explanation. There's this massive piece of data here that you have to try to explain. And the best one we have so far is galactic arm movements and cosmic rays causing more albedo. So more albedo means it's colder, less albedo means it's hotter. And there's a lot of agreement. This is the almost the same data, but not adjusted for pH. So these agree a lot, the orange one. And then the best one, if you had to put your money on, would be the black one. That's Chris Scotese. And he's put this together from many different sources. You can see he's got more granularity here. But keep in mind that the more you go back, the less certain we are. We're pretty sure actually that this low point was pretty low, that it was pretty cold 450 million years ago. This is that maybe galactic arm movement here, but maybe other interesting cosmic effects that we might be able to learn more about in here. And the reason we like the black one is that it ends low where we actually are now. So if you put all these data together, this is the most accurate here, and these are much less accurate now. So it makes a little more sense to put your faith into the black one. All right. Now, if we had to just summarize this and say, you know, with a reasonable amount of certainty, this is about what we have, because any of this squiggliness could change. You know, in the next 10 or 20 years, we might learn more things, and this might get really well established or not. It might wash out. We don't really know. All we can see really is 4 peaks and 4 valleys right now. And then, you know, maybe in the future, we'll be able to put more resolution on that. Now, CO2 is a different story. You measure CO2 very differently, partially with stomata, and there are other proxies for CO2. And the black one, there's 2 kind of main proxies here. The black one by Berner, and this, you can see the envelope here is the uncertainty. And it's a tremendous amount of uncertainty. So this black one could actually be flat because we don't know. We're talking about 160 million, 170 million years ago. You know, you have to have some uncertainty. And the more you go back, the more uncertainty. About the only thing we really do know, and you can see there's a lot of agreement, is that CO2, you know, this is time going forward. CO2 is very high, possibly even higher than 7,000 parts per million at various points, because we've got this big envelope up here. Could have been 10 or 11,000 parts per million. Not a particularly big deal. And this is just the last 550 million years. That, you know, 2 billion years ago, there was a lot more. There was like, you know, 13% of the atmosphere or something. So somewhere up here, and it went down. That's about all we can say. And then they all kind of agree that right here at 300 million years, there wasn't much CO2. Yet there was still enough to sustain life. And it wasn't so cold that it was icehouse Earth. Icehouse Earth, possibly there was a bit of an icehouse Earth right in here. But here's CO2. And if there was an icehouse Earth, it was not caused by lack of CO2. There was plenty. You know, temperatures are way down right here, and there's tons of CO2. So here, CO2 is at a low point. Then it either went up and then back down, or it didn't, because this orange reconstruction is also pretty good. And plate tectonics is what drives this. As we have more volcanism and more activity that mixes and gets CO2 coming out of the rock, you get a rise in CO2. And the other way we get is from weathering. You know, the weathering of the Dolomites, for example, or the ocean cliffs. It can take millions of years, but weathering will also take that CO2, the carbon locked up in calcium carbonate, and free it into the atmosphere just by grinding it and releasing it. That's how it goes up. And the way it goes down is what? How does CO2 go down?
To the ocean.
Shell making. Specifically, shell making. Tiny shrimp making shells out of calcium ions and CO2 in the air coming into the ocean. This is shell making. And then this is laying down sedimentary layers and locking up CO2 in rock. Okay. So here we don't know whether it's up or down, because this orange reconstruction is pretty well respected as well from the carbon isotopes. So it's one of these two, and it makes no sense. You know, someday later, we're going to know more, and we'll say, this black one was actually the right one, or no, the yellow one was actually the right one. So statistically, it makes, oh, so I'm going to come back to that. This is I forgot, another version of the same data by Willis Eschenbach. So life flourished at these very high CO2 levels, especially the Cambrian, and plants took over the earth in here. In the Permian, 280 million years ago, it was temperatures were lower probably than they are now. And the question is, how did CO2 manage to stay above the 100 parts per million where plants die? How did that happen? Is there some feedback that causes that? And I think the answer is we got it on the first day. There's just tons of CO2 here on Earth. It arrived, when Earth was put together. There's always been a lot of CO2. And so pretty much by luck, we've always had enough CO2 to sustain life in plants. And it's simply just the minimum that we can't even get to because there's so much. Right now, I want to go back to this. It statistically doesn't make sense to split the difference. It almost never does. So when you hear about splitting the difference, it's usually wrong. But because we have no way to choose between these right now, I am going to split the difference just for educational purposes. All right, so forgive me. And that will lead us to this. This is, at a high level, if you squint, this is the correlation between CO2 and temperature over 550 million years. Is there a correlation?
CO2, 4,000 West temperature.
I mean, if you want to cherry pick, you could say, oh, look, CO2 is going down here and temperature is going down. But most of the time, these are absolutely unrelated. Right? You just can't say that there's any correlation. Now, to get closer to the present, this is the last 66 million years since the dinosaurs died from the asteroid impact, you're going to have better quality data. So let's zoom in on the Cenozoic. This is a construction by Javier Vinos. During the late Cretaceous, that's back here. Despite the asteroid impact that killed the dinosaurs, temperatures were very high while CO2 was very low at about today's level. Then during the Eocene, this is kind of left over. Remember that the meteor impact that killed all the dinosaurs was not a climatic event. It was a very local, 20-year or something. It only takes a few years to kill most of life event. So it really didn't have anything to do with the climate. And then it kind of bottomed out here at about 58 million years. And then it just goes up. Is it driven by CO2? Well, that's hard to say, but here they are kind of, going in the same direction at the same time. Okay. Then here CO2 peaks, and you can see there are these little peaks in here. You see these little spikes in here. And I don't know anything about this. Is at the resolution of millions of years still. But here, temperature goes down the entire time as CO2 is kind of wiggling up and down and back up. Until we get to, so there's not much correlation here. And in fact, you kind of can see an anti-correlation, a negative correlation in general. And then here at 33 million years, what happened? 33 million years ago. 33 million years ago. 34 million years ago, we had this is called the Tethys Sea, and most of the equatorial flow went in this way, as we remember. And then when the Mediterranean closed, all the warm water coming around from Indonesia went south and created the Mediterranean climate that we have now in South Africa. But in my view, I believe that much of that hot warm air was able to then escape over the top through the wind, through storms, over the top to Antarctica, and then escape down and out, up and out over the pole to space. And so we had this freezing of Antarctica is what happened. There was land there, but that started the freeze. That started carrying energy to the poles and starting ventilating the heat, which froze Antarctica. And so temperatures plummeted. And we saw that in the animation several weeks ago. Temperatures plummeted quickly. This is like in 1 million years, Antarctica built up a couple of miles of ice from heat ventilating out over the pole, moving heat out because the heat was trapped before. Okay, and then after 1 million or 2 million years, it came to equilibrium. And so that was set. That's the southern exit. And then over some time, it went back up. Temperatures went back up again. And then they kind of cruised along for many years until here, right here at 14 million years ago. What happened? Let's go back here. The Isthmus of Panama, this was all open. 14 million years this closed. And that formed the Gulf Stream. And the Gulf Stream started up right here. And that warm water could now send heat to the Arctic to escape, and that froze the Arctic. And so this is the consequence of that event, is 14 million years of winters establishing themselves at the North Pole and creating permanent ice that this is the beginning of the ice age. This is an ice age now we're in because that happened, because the heat is able to get out. Okay. And all these little squiggles you see are interglacial periods, like we talk about all the time. This is a much bigger picture than most of when we talk about glacials and interglacials. So there are hundreds and hundreds of glacials and interglacials in here on the way down. And you think of it as we go down, we are just getting longer and more and more ice in summer. Summer ice is increasing as you go down into an ice age. Does that make sense? The more summer ice you have, because in winter you always have ice, the more summer ice you have, the more you're in an ice age. The ice wants to form, as we've said. So that's why we're in an ice age, because the summer ice is indicative of the heat flow, the heat escaping to get out. All right. And look what happened to CO2. Well, nothing special. You know, this is plate tectonics doing the work. Everybody see that? Now, for the last 2 or 3 million years, I mean, plate tectonics moves in periods of like 10 million years. So in the last couple of million years, there's no change in plate tectonics, really. So now we're back to this diagram, which we've all seen, and I want to explain what's going on. If you really want correlation, look at the last 800,000 years. And these are equivalent. This is 800,000 years of the same data. This is from the Vostok core. Ice core in Antarctica that is, I don't know, 1.5 miles long or something. And if the lines are thinner, it helps because temperature is in red and CO2 is in 2. And so what do you see? You see more red on the left and more blue on the right, right? This is what we're looking for. Red on the left means temperature moves first. Blue is a lagging indicator. CO2 follows temperature. Blue is always on the right. Do you see that? Except for one time. This is just zoom into the last 400,000 years. Here's one time where CO2 led temperature. And the rest of the time, the red is on the left. Right? And this might even be a mistake in the data, or it might have happened. But certainly you can't say that CO2 causes anything. In fact, CO2 lags generally by about 800 years. This difference here is about 800 years as CO2 comes out of the oceans as it warms up, and CO2 goes into the ocean as temperature goes down. We're going to learn about that in a second. What you see here, as we know, is eccentricity. Right? Anybody who tells you that CO2 is driving, really? What's driving these regular 100,000 year peaks? CO2? Honestly? You know, it just lines up exactly with high eccentricity. So we know what's driving temperature, and temperature drives CO2. Now, the alarmists know this. Even the IPCC knows this. It's called the lag, the temperature lag. And so they use various tricks to try to draw your attention elsewhere and get around it. Here's one of them. They separate the graphs, and then they paint this graph with big red. So you're looking down here and you don't realize it's very hard to tell that CO2 is lagging in this graph. You'd have to really use a ruler or something to figure that out. Looks like they're correlated. And then you can make the argument that because they're correlated, that CO2 is driving. This is what Al Gore does. Okay, they like it when they're separated, right? Or you can separate them a little bit and try to show that the blue is on the left and the red is on the right. Well, is it the blue on the left? Oh my gosh, look at that. Look at that. The blue is actually coming first here. And the peaks of the blue are a little, this is CO2 and this is temperature. The peaks of the blue, look at this. This is just a little bit ahead of the red. I mean, you have to, it's easier if you align them, but you can see that the peaks here, just a little bit ahead of the red, that it looks the other way. So what's going on here? Anybody know? What's happening here? Come on, someone say it.
Corruption.
No, come on. It's obvious. Come on. If I say it, you'll go, oh yeah. Oh, geez. I was blind.
It's also the scale.
Look at the x-axis. Time is running backward. They flip the axis.
Oh, yeah.
Oh yeah. So time is backward. This is today here. This is back in time. Yeah. They do this all the time. In fact, they do it in textbooks to fool school children. And you notice right away, I mean, that the straight up peaks are going the wrong way, right? This is the way it looks. The peaks are really going up, not down. And here it looks like the peaks are going, there's dramatic down. And that's because it's backwards. They're running time in reverse here on purpose to try to show you that CO2 leads temperature. It's worse than this. They really play tricks with this stuff in the textbooks and in lots of papers. This is from a paper. Okay. This is just absolute nonsense.
Yeah, it's just
this is today here. Okay. It's not statistically acceptable to run time backwards. It's against the convention on representing data. Okay.
So convention's always out the window then.
Look at this. Look at this. They're pointing it out right here. They're pointing it out. CO2 leads temperature. Look at that. Except the time is going backward again.
No, it's not.
Yeah. That's age. Years. Time is going backwards. And so they're just, it's just lying. If your data doesn't fit your theory, then smash the data in some way to make it at least look like it fits your theory, but it's not, it doesn't. So, and Al Gore does this all the time. Honestly, I really don't know if Al Gore really understands what he's doing or if he just gets fed from people and they know what they're doing to him. I'm not sure. This is a graph we've seen before for the 20,000 to 10,000 years. Time is running in the right direction, fortunately now. And except for the older Dryas and the younger Dryas periods, which we're going to talk more about in another class, temperature always leads. Red is first. Red is first. Red leads. CO2 lags. Now we'll look at this last level place. It's called the Holocene, and this is a graph that Javier has made, and they're in opposite phase. It's anti-correlated. When CO2 goes down, temperature is going up. When CO2 is going up, temperature is going down. The IPCC does not like to talk about the Holocene because it's very inconvenient for them. They went in opposite directions. Whenever you see a kind of figure 8 shape like this, that's anti-correlation. That's negative correlation.
Oh.
All right, so that's not very good.
Right.
Yeah. Any question? No question? All right. So there's there is correlation. There is, but temperature drives, and that's Henry's law in action. So who knows what Henry's law is? Do we have a chemist here? Henry's law, somebody? Henry's law is really simple. It says when there's a liquid meeting a gas, here's the liquid and here's the gas. At the boundary, at the surface of the liquid, the gas dissolved is directly proportional to the partial pressure of the gas in the liquid. And so it has to be at equilibrium, and it's temperature dependent. So as temperature rises, more gas comes out of, as a liquid warms, it outgasses, and as a liquid cools, it sucks in more gas. Any gas, air is a good example. More air goes into the oceans as they cool. And this is why you have more air in your cold water pipes at home. And when pipes freeze, which pipe freezes first in a deep freeze? The warm water pipe freezes first because it has less air. That means it has more water, and water expands when it freezes. So your warm water pipes will burst first, and the cold water pipes have enough air in them to absorb that the energy of the water expanding. Okay, so that's just physics. Air goes into liquids as they cool. Air comes out of liquids as they warm up. And that's exactly what we see right here. This is Henry's law. So temperature drives CO2 with a lag of about 800 years for Henry's law to equilibrate with the atmosphere. Okay? Now, when you look back 60 million years, you can't see Henry's law on a graph like this. Why? Because the 800-year lag is hidden. So they're tiny lags. If you looked at any one slice of this time and you looked in on a resolution of a couple thousand years, you'd see Henry's law all the way here. You just can't see it in a graph like this. Okay. Now, the computer models the people who design computer models have come up with a way to fool us into thinking that more CO2 is going to drive more higher temperatures. And it's a big elaborate machine, and I'm going to spend a few slides on it. And this is called the representation concentration pathways. If you're interested in government trickery, this is for you. They created different scenarios, and this is 8.5. And I forget what the 8.5 is. I used to know, but it means that basically business as usual, where essentially this assumption, 8.5, means that we just burn coal to make all of our power for the next 80 years. That's it. This is coal. This is just an assumption that we get all of our energy from coal, no natural gas, no anything else. And that's so that they can use it as an input to their models, which are sensitive to CO2, and get the temperatures they want out. And then they have other pathways that they occasionally use for other models, of course. It's all a bunch of rigorous nonsense because the scenarios don't matter. So when you hear people say, and you'll hear it all the time, well, RCP 8.5 isn't realistic. Oh, but our RCP 4.5, well, that's more realistic. That means that humans are able to decarbonize their economy pretty well, and we're able to successfully get a lot of that carbon out, and that'll drop the temperatures. And so let's use 4.5. No, that is nonsense because none of it has any impact on temperature. This is the normal computer generated output from putting in 8.5, which is coal fired, and then 6, and then, oh, look, we're saved. We're saved if we can just get it to RCP 4.5. Oh my gosh, the peak is in 2040, 2050, and it's only so many trillion tons. And then temperatures on Earth will be livable. Oh, thank goodness. And this is just designed to move money from taxpayers to government agencies. That's all. That's all these scenarios do. Nothing to do. It's great for NGOs too, but it's nothing to do with reality. And so this is where the action is. This is the whole story right here. People love weather disasters. Last week it was too hot in Europe. How is it this week? Oh, it's too cold. Well, it must be CO2 causing all the crazy weather. We can't burn witches anymore. So we'll just raise money for governments and NGOs and they'll solve the problem for us because it's all driven by, obviously, by CO2. There's no correlation. No one is saying it's not getting hotter. No one is saying that. Temperatures have been going up for 200 plus years since coming out of the Little Ice Age. They continue to go up as we near the end of the 65-year cycle. They're going up. That is not the reason that humans are causing it. It's all circular reasoning. They keep saying it's so hot, it's so hot. Sure, it's so hot. That is not causation. CO2 has nothing to do with it. There is no story here. It's just made up. And it's all based on feedbacks. So this is the final section here. You're all hanging in here, okay? Everybody still awake? Any questions? You can see it's mostly trickery and you can see there's no correlation, right?
Yeah.
If
Yep.
there was correlation, look, think of it this way, you know, if there was correlation, it'd be hard to get away from. They would be able to hammer us with it. But
I have a
they have
question.
to just dance in circles to try to get away from the problem.
I have a question.
Yes, Christian.
Is there any evidence pointing to the CO2 level triggering what should I say, the amount of
point.
plants and the mass? I mean, like, if you have more CO2, would you see more plants grow? To
We
put it
do.
simplistically.
I showed that last week. I showed the map.
Yeah.
Global greening. We've never had more green area on Earth since humans have been around.
So there is a correlation, definitely.
Oh, there's a huge correlation. We're causing, by putting CO2 into the atmosphere, we're causing plants to grow.
Yeah.
It's great.
Yeah.
The Sahara Desert is smaller by quite a bit. I don't know the number of square kilometers, but by 3 or 4% in the last 40 years, the Sahara Desert is smaller. Yeah.
Okay, thank you.
The Sahara Desert is remarkably plastic. It really moves. 8,000 years ago, it was mostly savanna. And I don't know how many years ago it was ocean, and there's whale bones buried in the sand in the Sahara. So feedbacks. The feedbacks in nature are almost all negative. Any positive feedbacks will just run away and destroy a system. A feedback means that if there's a small perturbation, it goes back where it was. A negative feedback means it goes back where it was. A positive feedback means if there's a small perturbation, it runs away. Just takes a little bit and then it runs. Okay. So a positive feedback would be in the explosion of an atomic bomb or a virus that takes over its host and kills it because it has no brakes. So for the few positive feedbacks in nature, there's generally some opposing force designed to contain it, or else it would just wipe out everything. And if feedbacks were positive in temperature, then the Earth would just be a hothouse and it would have stayed. There would have been nothing to bring it back. Right? Except that's not what makes the hothouse. What makes the hothouse is orbital mechanics. Right? As we know, it's the distance to the sun and it's the angle of the Earth, of the axis. So there's no feedbacks there that cause that. So if water vapor is such a strong feedback, how has the Earth recovered from hothouse conditions and gone cold again, time after time after time in regular 100,000-year cycles? How could that be from feedbacks? Does this look like feedback? It's not feedback. This is just going through spiral arms and making our way around the galaxy, or other celestial mechanics that move it up and down. It's the same as when the sun goes down at night and comes back up tomorrow morning. It's not feedbacks that do it. It's not feedbacks that are running your temperature thermometer up and down every day. Okay. So there is one positive feedback in climate science that I know of, and I want to explain it to you. It's the reason that we come out of ice ages quickly and go to hothouse or warmer conditions quickly, and they go down slowly. See that? We tend to go up fast and down slow. And that's even true at a smaller time scale. A lot of times we go up faster than we go down. See that? It's pretty regular, right? This is, of course, humans. So why? We know that this is from eccentricity. And we know that down here, when it's dark and cold, that the ice has an advantage. The ice is always trying to come down from the North Pole. The South Pole doesn't change much. So this is the story really of the North Pole, which is where the land is. And that's where the ice comes down. And we've had, a kilometer of ice over New York City 20 years ago, probably, I don't know how much over London, but maybe a kilometer of ice over London 20,000 years ago. And every 100,000 years, as the Earth orbit gets more round, ice marches toward the equator. And then we get to an ice age. All right. Once the Earth's orbit starts to come back and we get those longer summer days where as I've explained before, the sun has more of a chance to beat the ice back, we get a positive feedback loop where the ice is very bright, it's very white and shiny. And so down here, there's more albedo. What's albedo?
It's reflection.
Reflection of the incoming sunlight. So more incoming sunlight is reflected away. So there's less energy to heat the Earth. And as we get longer summer days, it melts the ice and exposes the rock. And the rock, it can be shiny, but it absorbs a lot more than snow. And that is a positive feedback that melts more snow, reduces albedo, which melts more snow, which reduces albedo. And so we go up pretty quickly. And when I say quickly, I'm talking about 3,000 or 4,000 years quickly, as the orbit gets a little more elliptical. And the sun has a chance every year to beat back more ice. And that feedback actually helps accelerate this. And on the way down, where the ice is creeping in, it doesn't work in reverse. So this is more like how the cycle would actually be if you had no albedo effect. And this is more with a kind of an accelerated albedo effect. Because if you think about it, this elliptical or round, the eccentricity, it's regular. It's like a top. It does not have this shape, right? This is momentum. Momentum doesn't have a J shape. It's going to have a sinusoidal shape. It has to. This is like the spinning of a top, okay? There's nothing magical that makes this into a J curve, okay? So the real bottom of these eccentricities is in between the peaks. And it's the feedbacks that changes the shape of that. Does that make sense? It's a sinusoidal curve. But also keep in mind, we've got obliquity running at a 41,000 year cycle that causes a lot of jagginess, right? Plus Jupiter and Saturn. So it's more complicated than that. But generally, what makes the asymmetry here is largely from feedbacks. Because it's regular. The asymmetry is regular. We have this sort of J curve over and over. So that's not Saturn. That's not Jupiter. Okay, that's not going to be obliquity. That's feedback. Okay. All right, and that's a little tricky. Now, when we talk about feedbacks in climate science today, it's a thought experiment. We assume that there's an instant doubling of CO2 instantaneously. It's a convention. What would happen if CO2 doubled right now? Okay, this is just a thought experiment, but at least one Nobel Prize has been won based on the stupid answer to it. As we've learned, the greenhouse effect really is real. from January to July, the Earth gains, the greenhouse effect is very real. It happens every night. It keeps overnight temperatures low, keeps overnight temperatures from getting too low, it keeps extremes, the overnight temperature from being too extreme. So that's the greenhouse effect right there every night. From January to July, the Earth gains 2.2 degrees. So if we could double CO2, and we did get an instantaneous worldwide increase of 1 degree Celsius, it would be a lot. It would be like having July temperatures in April and then some new extra hot temperatures in July. It would be a lot. 1% globally would be a lot. The good news is that there's no such thing as global climate, except maybe on the order of 100 million years. And so, or if the continents change, at least 10 million years. But that 1 degree would be a lot theoretically. That's why the UN can use it to say, yes, this 1 degree is a big deal because it's going to cause, through water vapor, more feedbacks, and we might get 2 or 3 or 4 degrees globally, and that would be bad. It would be bad. It would be bad. It's not true, but if it actually happened, it would be bad, but it can't. Okay. So if we doubled from here, from 420, oh, sorry. But a reason that this curve, let me go back. This curve that I've shown you before may not be right because it says how much warming you'd get from doubling CO2. And in fact, it's more likely to be quite a bit shallower than this and quite a bit less consequential. And we're very much on the flat part, so that if we doubled from here, it would be way out from here to, the amount we've already added from 280 to 420 has added very little. You can't measure it. It's not enough to measure. It's probably much shallower than the blue curve, and it's probably impossible for us to tell because it's so small. Okay, you can calculate these numbers all you want. It's just a thought experiment, but in reality, the observed temperature rise is almost all natural and it has nothing to do with CO2, okay, because it's been happening for 250 years. So this calculation from the greenhouse effect is probably wrong. And if we take it out now and double CO2, this is what all the computer models are about, going from 420 to 840. Now, just to go from 420 to 840 parts per million, it would take more than 100 years of burning nothing but coal, supplying 100% of the world's energy needs by burning coal for 100 years. Maybe if we worked really hard at it, we could double CO2. Might take 200 years. Okay. It's practically impossible. It is impossible. And it's projected, that doubling is projected to raise the temperature 1 degree C. Now, as we see, that would be a lot. Okay. But the equation that produces this number is wrong, as it's probably more way down here. It's probably very much flatter than this blue curve. As Javier says, CO2 is probably like the pilot light that just keeps nighttime temperatures from going down too much, and it always has. And raising it probably has such a tiny effect that we can't measure it. So it depends what the shape of the curve is that you're basing your thought experiment on. And if it's super flat, your thought experiment isn't worth anything. So, but no, they are not good enough with that. They have to expand it and turn it into something. So they do the thought experiment and continue it and say, well, after the instantaneous temperature rise, the first feedback is called transient climate response. You do not have to know this. This is government trickery. It's just kind of a side note. It's a theoretical calculation based on the climate system's response to a doubling of CO2, and it takes decades, tens to hundreds of years to play out. And it's just computer code. That's all it is. You can plug in any numbers you like. You all those RCP pathways, put in whatever you like for whatever number you want to get out. As long as it gives you the result your boss is looking for, then you're done. That's all you have to do. So that's transient climate response, is just a made up response in a world that doesn't, to a model world that doesn't exist, to an instantaneous doubling of CO2 that cannot happen. Oh, it gets worse. Now, the next one is equilibrium climate sensitivity. They've been calculating this since the 1980s. It's the long-term response of the climate system to a doubling of CO2. It accounts for all the feedback in the climate system, the changes in water vapor, clouds, ice, albedo, Henry's law, etc., ozone, etc., etc. It's calculated over centuries to millennia for the world to equilibrate after this instantaneous doubling, and it's completely made up by politicians. And this, you can tell, this could be $2 billion worth of research. I am not kidding, over the last 50 years on this one number. And it's just a political outcome. And so they've decided that it's in the range of, if we doubled CO2, it's just theory, that it would be between 1.5 or 1.8 to 5 degrees. And this is just so they can use it to scare people. It's a political product. CO2 can't double. This is just another tool to manipulate people because it lets them put the number 5 degrees in headlines, and we have to do everything we can to keep it to 2.0, the worst. This is the best it's all just made up. These numbers are all made up. Now, on the other hand, if you actually care about this, which doesn't make a lot of sense because CO2 probably isn't driving a thing, one guy, Nick Lewis, who's very smart, super scientist guy, kind of a gentleman scientist, has excellent statistics background, calculates the ECS between 1.5 and 2 degrees. And this is for doubling to 840. It can't possibly happen, but he believes that if this were unleashed on the Earth's systems, and this is a whole paper, you can read it. It's good, but it's wrong because it can't happen. And even if it did, it wouldn't happen. It wouldn't play out like this. And we're going to find out why later, because we're going to learn about the heat pump, which is where the reaction really is. Now, speaking of reality, and we're almost done here. This is the last little bit. Feedbacks in reality are net negative. The Earth doesn't have a thermostat, but the tropics do have a thermostat. And if you've been to the tropics, you've seen it. Low clouds form starting at 10 in the morning and are usually up and in pretty good shape by noon every day. And at night, they prevent heat from escaping. High clouds are mostly ice and increased albedo. And on balance, clouds probably have a slight cooling effect. And this is a thermostat, and I'm going to show you how it works. The temperature goes up at, say during a season or during a morning, it'll go up from here to here. And when it reaches 26 degrees, that's a tipping point. At 26 degrees Celsius, water surface temperature, water changes state and evaporates and creates clouds and storms. And this decreases the amount of energy arriving from the sun. This is spontaneous cooling that is a result of clouds forming. And then when it goes down enough, then the clouds might go away and then the temperature will go back up again. So this oscillation happens during the afternoons until nighttime, and then it goes back down again. And overnight, there often aren't any clouds in the tropics. And sometimes there are, depends on the pressure systems. But this general feedback mechanism here peaks at 26 degrees, and it doesn't let the oceans ever get to 30 degrees. The ocean temperature never gets to 30 degrees because it's just too busy making clouds at that point. There's too much evaporation for it. Because, with evaporation, if you blow on a wet thing, it's cold, right? So it's cooling the earth. So here it is from a satellite. We see where the strongest sun is, there's the most cooling where you have water. 56% of all the energy arriving from the sun arrives in the tropics. There's a massive cooling effect as the water reaches that 26 degree threshold and evaporates. Evaporation is cooling. So recall that evaporation is a state change that will require a lot of heat. We're going to go into this next week. A lot of energy to evaporate, and evaporate cools the oceans, and it sends that heat up into the clouds. And that's called latent heat from evaporation. And when it gets up to the top of the clouds, it condenses out and turns into droplets and releases the heat up out to space. This is what we saw last week. Most of the heat transport, I mentioned it last week, but I want you to understand, most of the heat transport from the surface of the Earth to the top of the atmosphere where it can get away is done through latent heat of evaporation and then condensation higher up. It's still the random path of that long-range photon I talked about last week, but it's using water vapor to move the energy up through the air column. So the land, on the other hand, gets very hot. It doesn't really store heat, but it can't really release the heat until night. So during the day at noon, you see this picture. The land is very hot, the deserts are very hot, and the ocean is under cloud cover, and its temperature doesn't change. It has a thermostat. Okay. And so if we look at, Javier has shown that if you look at the projections of the CO of the IPCC, they say, well, yes, there's one, if you double, here's your doubling of CO2 to 800 out here. If you double CO2, you get 1 degree of rise from the greenhouse effect, which is wrong, but no matter. You get 1 degree, and then you get these feedbacks from water vapor that maybe triple that and give you these extreme temperatures, and you get 3.0 ECS, or it's even more with 4.5 or 5, whatever number you want to make up here. This is all computer models. But he shows that if this is true, take a middle one like 3.0, like 3 degrees. If it's true, then those models have to reflect reality running backward in time. And if they did, then when CO2 was lower, the feedbacks would be more, and it would just be too cold. Those temperatures didn't exist. When it was 280, 150 years ago, when CO2 was this much down, temperature was not that much down. And you can't say that the physics changes. The physics can't change. So if there are any feedbacks, if CO2 has any effect on temperature, it's small. And if there are any feedbacks, they're probably negative. So giant feedbacks like this is just the common narrative that's used to sell you an alarm. They don't exist in nature. And so this is easily summed up by Le Chatelier's principle. Most feedbacks in natural systems are negative. There are no tipping points. There have been a few tipping points in the past, and we're going to talk more about some in the future class, but there aren't any real tipping points now. All right, that's my climate theater for today. Questions, confusions, reactions?
Yeah, I was just going to say on the back of what Christine was saying, when you had shown the graph of life on Earth and the amount of CO2, I thought it was funny because really, if we had a long-term plan, it would perhaps be to just put as much CO2 into the atmosphere as possible, because it seems to drive life and plant growth, and most people would probably think that's a good thing.
Certainly, we're in a CO2 famine right now. Yeah, we're lucky that we've been able to put some CO2 into the air. It hasn't probably mattered much, but if we could double it, yeah. Sure. That'd make a difference. Anybody like, I don't believe that stuff. That's not, you're cherry picking. I don't believe it.
I have a question. I'll see if I can articulate it. It's Paul here. Sorry, I'm finding it difficult to articulate this. Before the jet stream and the Atlantic Ocean was running across, the heat.
Oh, you mean the Gulf Stream?
Gulf Stream. Thank you. The heat was escaping through the South Pole and out through the bottom. Is that correct? Of the planet?
After 33 million years, after the Middle East came closed.
Yes. Mm-hmm. It was going. The heat was escaping, but heat rises. Is that a stupid thing to think?
Oh no, much of it gets transported over the atmosphere, and as we're going to see in the heat pump, a lot of heat comes into the poles through the atmosphere, and that's why there's a temperature inversion on the land in the poles. It comes across above the land, above the ice.
It comes above it. But if
Sure.
the Gulf Stream, if the Gulf Streams are pushing north, and say for example to the North Pole, then why is the ice not melting?
It is. If you look at a picture of winter ice, you'll see a direct incursion in the
But it's actually growing, they say.
well, growing has to do with the orbital mechanics. The
Okay.
ice, it's not growing very fast. You know, our precession is a 13,000 year, 26,000 year cycle. I mean, it's, you know, there isn't much, any growing of, I think you're talking about Arctic amplification, where we've been having some Arctic melting over the last 20 years.
Well, you say 20 years ago, Al Gore, he was saying, oh, in 10 years, 2010,
They'll
10
all be
years,
gone.
there'll be no polar bears, there'll be nothing there,
Right.
blah, 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 blah. But it's
Right.
actually grown since that time.
That's not quite true. And we're going to go over that. What has happened, Corin, is that winter temperatures in the Arctic have risen a bit. Summer temperatures haven't changed. Summer temperatures over the last 20 years are flat, but winter temperatures have gone up a bit. And this is Arctic amplification. And we'll talk about that, I think, in 2 weeks. It's
So that's like the albedo is reflecting the sun back.
No, it's complicated, and we don't know yet really what has caused it, but it's just winter temperatures, and it's not a heck of a lot.
Okay.
It's the kind of thing that 20 years from now could be completely reversed. And remember,
Yeah.
there's a 65-year cycle, and we're toward the peak of it. So there's some uncertainty about understanding the cause, but it's well within normal range of variance, well within. And it's just winter temperatures. We have milder winters for about the last 20 years, and it maybe means nothing. We don't know.
All right. Okay.
But back to the Gulf Stream, if you look at summer temperatures, if you look at winter ice over the North Pole, winter ice, when it's maximal ice, you see that through the, where's my Greenland? That's the Pacific. That's where I'm. Hello. Let me see. Oh, this is backward for me. Oh, I see. Because I see a mirror image.
Okay.
I see a mirror image that you guys don't see. This is Florida, right?
Yep.
Yeah,
Yeah.
I'm sorry. I see a mirror image. So because my face is mirrored for me.
Oh, well
So
done.
the Gulf Stream takes water, and this is the Fram Strait between Greenland and, well, actually, sorry, this is the, God, I'm
right.
backwards. Is this Iceland here?
Yep.
Okay,
That's Iceland. Here's the Fram Strait up here.
thank you.
Gosh, it's so backward for me that you'll see that this flow of water here makes a huge incursion into the ice. So even though it's all ice all around, the warm water is just ramming into it and melting ice. So every winter you get a lot of heat
So it's
coming
like
throat
it's
the
cutting a groove
this
in it.
current. And that's what heats the UK.
Not at the moment.
Yeah, but in this Gulf Stream comes over and keeps the UK much milder than it would be at the same latitude, in Vladivostok. It's much, much colder because of that hot, warm water coming through the Gulf Stream is warming this whole region.
Mhm.
And that's where there's much less ice in wintertime
Okay.
because warm water. Okay.
Thank you very much.
Next week, we're going to start in on the heat pump, which is how we move heat. The climate of the Earth is not global. There's no global climate, except maybe when there's an ice ball. 750 million years ago, there was a global climate. But the climate of the Earth is latitudinal. And it's based on pressure systems and currents that separate, and mountains and valleys. That's really what, the shape of the continents and the movement of heat is what creates our climate. And that's why people are confused, because it's not simple and it's regional and it's hard to figure out. Yeah, Michael.
Hi, David. Yeah, sorry I come in a bit late. So I've done study on meteorology, and something I never got was latent heat and how heat was captured in water vapor and then released again in rainfall and creating wind. And this is kind of unfolding that for me a little bit.
Oh, there's more next week.
Okay.
Yeah, it's all stacking up, because you think about the random path of the photon that we talked about last week, and then you start to look at evaporation and convection and the movement of energy through the air column. It's all going to, I hope, come together over a couple of classes.
Yeah. So that's sort of like kind of unfolding a question that I've had in my mind for years, and how it creates wind as well, because I studied meteorology to go sailing, and it's just one of those concepts that I never really got, that water vapor would bring in heat and then release it again when it turned into raindrops and help create wind.
Yes, but remember, wind is created by pressure differentials, right? Where wind goes from high pressure to low pressure.
Yeah.
Air moves from low pressure to high
high
pressure to low pressure.
So when we're out at sea and we see like a cloud bank coming towards us, that's time to start reducing sail, because there'll be a heck of a lot of wind.
Yeah.
Coming towards you. So,
yeah. So the water vapor is carried along. It's not a causation of the wind generally, unless it can cause a temperature differential. So wherever you have a temperature gradient, you can have a pressure gradient, and that gives you wind.
Yeah. Excellent.
It's all about gradients. If you really want to sort of unpack all this stuff, you start to learn about, it's all about gradients. That, and the IPCC never talks about gradients, because that's where the real drivers of things are, and they don't have any interest in the drivers.
Yeah, so I watch the synoptic charts across the Atlantic and read my weather that way, rather than getting it off the BBC, off the Weather Girl.
Cool.
Because it's all about, like you say, about the gradients.
Yeah, right. You can see these fascinating maps of wind, speed, and pressure changes. Right, and it's really complex, as anybody who's flown a hot air balloon knows. There are many layers, and there's all kinds of things going on at different layers. You can be 100 feet up and go the opposite direction. Right, so there's some chaos in there, some chaotic mixing, and there's a lot of laminar flow, both. If you have laminar flow going this way, then you have chaotic mixing in between at the boundary.
Okay.
Right, and so a lot of that is unpredictable. It's kind of why balloon pilots have to do it by feel, and glider pilots, they have to do it by feel, because they can't see it, and whatever was there 2 minutes ago isn't there now.
Yeah, we see it in the sky, don't we? The wind will be coming in one direction, and we're looking at the sky, and the clouds are going in a different direction.
That's right. That's right. And some of this is predictable, but at the boundary layers, it isn't. It's chaotic. Okay, anything else about correlation and causation? I hope I've destroyed any notion. Katrine asked, what about the hot spot in the tropical troposphere hotspot we are supposed to see that isn't there? And that's something people have heard several times. So I'm going to post a great video on that in the resources section in the next half hour. So you'll see that. And it's really good. It just destroys one of the predictions of the IPCC is that, and NASA, is that as the Earth warms from CO2, the tropical troposphere is going to heat up. And no, it hasn't happened. There's a bunch of other predictions that haven't happened. But it's a really good video, so I'll post it. Anything else, anybody?
David, if I can ask a question, one thing that's sort of puzzled me for a bit is the Earth radiates a more or less constant amount of energy. So, well, not exactly, but you know, for the sake
Over
of
time,
argument,
yes. If you would
Yeah.
say over time, then I would agree.
yeah, over a year, say.
No, because there are things that can trap heat in the oceans for, decades.
Oh, that's true.
You know,
Yes.
heat
Let's
can
say-
go down into the ocean and not come out for 2 or 3,000
yes.
years.
Right.
But
So-
just say over time, yes.
Over time, right. Now, to me, that means that there's a maximum amount of absorption of energy that greenhouse gases can do. And once they reach that, they've absorbed the energy the Earth is emitting, any greenhouse effect is going to stop.
No, there's a fundamental error in that, and I addressed it last week. That's okay. But can you think, remember did you read the homework piece last week?
Yep,
The journey of the photon?
right, yes,
It's not trapped. Or the sweater analogy?
yes,
It's not trapped. It's delayed. So the atmosphere or the greenhouse gases increases the residence time, but it doesn't stop those photons are out in about 10 milliseconds anyway. They're just hanging around 10 milliseconds longer than they would if they went straight out.
all right,
So the path might be 10 kilometers straight, but they might go 3,000 kilometers in the sweater in the lower atmosphere to go that 10 kilometers. And that increases the temp. That is the greenhouse effect. And there's no trapping and there's no buildup.
So is there any constraint on the greenhouse effect? Physically?
Well, I think I'm not sure if this answers your question, but Javier says, and Will Happer says, it's like the pilot light that just keeps the overnight temperatures from escaping too much, and it doesn't really do anything else. There isn't more. It can't do more because it's already saturated.
Right, so it's just controlling the rate.
It's increasing the residence time enough to make overnight temperatures bearable for life. If we
Right.
didn't have it, we wouldn't be here to talk about it. That's all it does. It's the only thing it does is manage to keep overnight temperatures reasonable through this longer path, residence time, and it has no further effect.
Fine, thank you very much.
That's how we think of it in the camp of Will Happer and Javier Vinos.
Right.
And I'm not a thought leader, I'm a follower, so I'll go with those guys.
Yeah, well, I'm only at chapter 5 in Climate.
Well, you're
Past
doing
and
great.
Present and
It's a big
Yeah.
project,
It is.
and
Yeah.
it's got small print, so you need your reading glasses.
Yeah.
And a bright light. Right. Remember, this is just the residence time, and all of this feedback stuff and the tipping points is just part of the climate industrial complex. It's like eugenics. It's just made up to serve a purpose. Really? Sounds science-y, but it's not science. I will put the tropical hotspot video up. We will all prepare for the heat pump. The heat pump is really chapter 10 and 11. It's ridiculously technical, so I'm going to try to make it as simple as I can. That's my goal for the next two classes, is to, now we're kind of out of the nonsense zone and into how things really work. So any other questions or comments about the nonsense CO2 stuff? Because I really people talk about the RCPs and this, and it just doesn't matter. So and the feedbacks, I just have no tolerance for it, because you're just arguing against something that isn't there. It's not worth spending much time on.
I think on that subject, there was a thing I heard a while ago about Venus having a tipping point, like we're going to end up like Venus, and the gases get to a certain point, and then it's just the whole planet's like a storm. Now, I think I believed that at the time. It reminds me of that, but maybe now I'd think I was complete rubbish.
Venus's, I was going to put a whole thing here on Venus and Mars, and Venus's climate is so complex. It would take me 6 months of hard work to dig it out and try to explain it in a simple way. There are huge storms on Venus. The density of the atmosphere at the ground is 90 times what we have here. The greenhouse effect is much greater, and the dynamics are so different from what we have that there's no possible comparison.
Yeah,
It's not even close. Once you start looking at it, it's just you just say, oh, okay, this is just too much. There's no way. There's nothing simple. This is not simple. Mars is fairly simple. Mars has a very light CO2 atmosphere and about the same length of day as we have. And it's just brutally cold at night when you're out of the sun, because there just isn't enough residence time to make temperatures comfortable. So it's about, as their hottest time during the day is about like Siberia in the middle of winter. And that's about as good as it gets. Terrible place to go try to spend time. Really bad idea to send humans to Mars. Really horrible idea. I mean, if you're going to send people on some mission, send them to Antarctica and see how they survive there. It's really, really hard. And there's so much nonsense. There's so much, all the money is being spent so badly right now. We should
that's what I thought was funny with the thing CO2. They're focusing on CO2, but it's literally like the thing that creates life and greens, with agriculture and greening deserts. It seems like a really positive thing. And they've literally turned it on its head and said,
yeah. No, we're spending trillions of dollars doing stuff that just hurts poor people and has no benefit. Really bad. I mean, mining for all the minerals required, and now they want to mine the seafloor to get the minerals to make the wind turbines. It's just circular reasoning, and it's just a big money grab. Just look for the incentives. We have no money, those of us who study the climate. When we get together, those of us who study, we just talk about climate and science all the time. And when those guys get together, they just talk about money. Because that's the game. That's the game they're playing. And they're winning.
Have you ever challenged anyone to debate in a sort of senior position?
They won't. They just call you names. They just say you're wrong. Will Happer's an idiot. You're wrong. You have no authority. Where's your climate science degree? How many papers have you? They just all this. It just goes on. They have no. I've had people on Twitter say that Javier Vinos is an idiot. He doesn't know what he's talking about. He's wrong. Oh, really? Can you show me the sentence that's wrong and why? No, it's not even worth my time, they say. I'm too busy decarbonizing the world. I don't have time to show your silly arguments and do any debates. We're past that time. It's time to go fix the problem. Geoengineering. Whatever makes the most money from governments. Oh, we did pretty well today. We got through a lot. Anybody, anything else? Anybody want to, give feedback on how things are going, or it's too much high level, or it's too fast, or it's too slow and boring, or?
Yeah, today, as Paul here, sorry, I haven't given my camera on. I thought it was very informative today. Thank you very much.
Sure.
Yeah,
As do I. Thank you, David.
Sure.
Because I'm used to the Tuesday class.
Ah.
So I'm a traitor.
I'm so much better by Thursday. I've really thought
you're smoking.
I've thought it out by Thursday.
Yeah, I mean, yeah. But it's very good. Thank you very much.
Sure. Well, this was the one that will be recorded. Also, I will appreciate anybody who wants to talk about. All these recordings are going to be here. So this whole class is here. So we could run, for example, cohorts of people through this, like city council member types, and people who want to get educated. We could use this as a resource for people. I just want to figure out a business model for it. And as I've said, I'll come run workshops if people really want to know what's really going on, which, that's not where the incentives are. So, but if people are neutral, I want to try to figure out how to scale this. And that's why I'm taking care to make good videos. So if anybody has ideas about how to do that, please reach out.
All right. Thank you very much, David. Speak to you
Thank
later on.
you. All right. I'm stopping.